Hey everyone! All right, so the title for today's notes is inverse functions. So what is an inverse function? Well, an inverse functions are functions that undo or like reverse another function. So what does that mean? I can go ahead and kind of do like a little quick example here off to the side. So like, let's just say we have a function f and it is defined as like this mapping here. And my mapping is going to have an input of 1, 2, and 3, and it's going to have an output of, I don't know, -1, 0, and 1. All right, and in my function, I'm going to go ahead and define that when you have an input of 1, your output is 0. When you have an input of 2, your output is -1. And then when you have an input of 3, your output is +1. All right, so if that's my function f, then the inverse of this function would be the function where whenever you have an input of -1, your output is 2. Whenever you have an input of 0, your output is 1. And then whenever you have an input of 1, your output is 3. So you notice here that these two are functions of one another because, as our definition states, they are functions that undo or reverse one another. All right, so obviously the functions that we're going to be working with today are not going to be as simple as like these mappings. They're going to be actual like equations where you're going to need to know how to solve algebraically for an inverse. The 4 easy steps to solving for them are given to you right here in these notes. We'll do some examples of solving for inverses algebraically, considering the domain of inverse functions, and then also verifying functions. So if I give you two functions, can you tell me if those two functions are inverses of one another? All right, so let's go straight to it. So again, the definition of an inverse function are just functions that undo or reverse one another. The notation that we will be using is this right here. So if I give you a function f of x, the inverse of the function will be written as f inverse of x. This inverse symbol here looks like a -1 to the x to the power, like a -1 in the exponent. However, please do not say that as f -1 of x. It is, this is an x, by the way. I just realized that's kind of bad writing there. That is f inverse of x. So that's the notation that we use. All right, and then like I said, 4 simple steps to solve for an inverse algebraically. You first want to go ahead and replace f of x with y. And then you're going to interchange or like swap the x and the y variables. Then you're going to solve for y. And then lastly, you're going to rewrite y back again in inverse notation by using f inverse of x. I know those probably sound like ambiguous right now, but once we do some examples, hopefully they make sense. So let's jump right into it. Let's find the inverse of two functions. We're going to be going and heading and doing 2 examples right here. So I'm going to draw a line down the middle. Let's do example 1 off here to the side first, and then we'll do example 2. All right, so example 1, given f of x is equal to, let's do 4x minus 8. I want us to go ahead and solve for the inverse of this function. So as my steps state, what I'm going to first go ahead and do is replace f of x with y. So what does that mean? Wherever I see f of x, rather than writing f of x, I'm just going to write y is equal to 4x minus 8. All right, step 2, what are we doing? We're interchanging x and y. What does that mean? Well, that means that wherever you see a y, you're going to replace it with an x, and wherever you see an x, you're going to replace it with a y. You're going to reverse, you're going to swap those 2 variables. So this will turn to x is equal to 4y minus 8. All right, after you've done that, you're going to now solve for your new y. What does that mean to solve for y? That means to get y by itself on one side of the equal sign. So I'm going to add 8 to both sides first. This will turn to x plus 8 is equal to 4y. And then my last step to get y solved for is to divide both sides of this equation by 4. Remember, the 4 needs to be divided to the entire left side, not just the 8 and not just the x. All right, on the right, those two simplify out to 1. So you're left with y is equal to x plus 8 over 4. Now that you have solved for y, you're just going to rewrite y with your function notation. So you're going to say f inverse of x is equal to x plus 8 over 4. And that is the inverse, that is the undo or the reverse function of your original function. So like going back to the mapping, this tells me that like my inputs and my outputs should be reversed here. So like, for example, if I were to input a value of 2 into my original function, this would be 4 times 2 minus 8, which simplifies down to 8 minus 8, which simplifies down to 0. So whenever I have an input of 2, my output is 0. In my inverse, those should be swapped. So whenever I have an input of 0, my output should be 2. Let's go ahead and verify. This would be 0 plus 8 over 4, which is equal to 8 divided by 4, which is equal to 2. So we do indeed see that our functions are inverses of one another. They are like the undo or the reverse of the original function. My inputs and my outputs have swapped. Okay, so that's what an inverse is, and that's how you solve for it algebraically. Let's go ahead and do one more example. This one will be a little bit more complex. It's really just the algebra that will get more complex. The steps are exactly the same. All right, so let me go ahead and give you a new function. Let me tell you that f of x is going to be equal to x plus 4 over x. So you notice here that you have your variable x 2 times. So you're going to have to replace it with a y in 2 different locations. But that's the second step. Let's do the first step. First step is to replace f of x with y. So this is going to be y is equal to x plus 4 over x. Step 2 says to swap or interchange your variables. So I am going to put an x on the outside is equal to a y plus 4 over y. Right? All I did was swap my variables there. And then now I want to go ahead and solve for y on my new equation. So first of all, the denominators, we do not like denominators in our equations. We do not like fractions. So let's go ahead and, oops, sorry, I dropped my pen. Let's go ahead and eliminate that denominator by multiplying this entire equation out by what my denominator is. So on my right-hand side, these eliminate out, and then you're left with y plus 4 is equal to yx. Those are being multiplied. Now remember, you want to solve for y. You want to get y on one side of the equal sign. So let's go ahead and move this y to the other side of the equal sign. So this will turn to yx minus y is equal to 4. Do we all understand what I did there? All I did was subtract y to both sides of the equal sign. All right, and then again, your goal is to solve for y. So I noticed that on the left-hand side, there's a GCF there of y that I can like factor out, and then you would be left with x minus 1 is equal to 4. Do we all understand what I did there? You take out the variable y because they both share a y, so you can factor that out. Again, your goal is to get y by itself. You need this by itself. So now I need to move this to the other side. How can you do that? Well, you can go ahead and divide x minus 1 to both sides. On the left-hand side, x minus 1 divided by x minus 1, that eliminates out. And then you're left with your, I don't have any space, so I'm going to bring it up to the top. Your y is equal to 4 over x minus 1. And 4 over x minus 1 can no longer be simplified. You've now solved this equation for y, so you can rewrite it in function notation. So this would be f inverse of x is equal to 4 over x minus 1. And that is the inverse of my original function. That is the undo or the reverse of my original function. In my inverse, you should also notice that there is some restricting in the domain that I have to do. Like this inverse is not defined for all values of x. The domain of this one would be all real numbers. However, you need to exclude the value of x cannot equal a positive 1. And why is that? Because remember, you cannot have a value of 0 in the denominator of a fraction. And yes, I do want you all to get used to and comfortable with domain and excluding domain, especially with inverse functions. Another property of inverse functions is that pretty much the domain of the original becomes the range of the inverse, and then the domain of the inverse is the range of the original. So that's another special property between functions and their inverses. Their domain and their range get swapped, which if you think about it in the mapping that I did earlier, you notice there that your domains become your ranges and your ranges become your domains in inverse functions and their original functions. All right, so that is how you solve for an inverse algebraically and how you restrict the domain of the inverse. The second part to these notes that you all need to know how to do is how to verify inverses. And what do I mean by that? Well, let's go ahead and copy down these notes. So this will be still the same title, but just like another bullet point. By the way, I'm using a new... I don't know if I said this already, but I'm using a new app to take notes. I don't know if you guys noticed. I don't know. I kind of like it because it has like this little laser pointer thing, but I don't know. If you have any feedback, let me know. Okay, so second part of these notes. Verifying inverses. So you guys already know how to solve for an inverse now, but how do you verify inverses? Well, two functions, let's call them f and g, are inverses if f composed with g of x is equal to x, and g composed with f of x is equal to x. All right, so this connects back to what we just went over in yesterday's notes. But yeah, so if the composition of f composed with g is equal to, simplifies down to just x, and then the composition of g composed with f also simplifies down to x, then you know that f and g are inverses of one another. So this is not, these are going to be questions where it's going to, what's given to you in the start is going to look a little bit different. All right, so let's do an example. We'll do two again. If you don't need to, then you can stop the video, I guess. But obviously the second one will be a little bit more complex, a little bit more algebra complex. So I would stick around if you want to work on some algebra skills. All right, so these are directions where it's going to say verify algebraically that f of x and g of x are inverses of one another. So like, let's say, for example, I give you the function f of x is equal to x minus 7 over 2. And then I give you g of x is equal to 2x plus 7. All right, now just because the numbers look like similar and things like that, you cannot assume that these are inverses of one another. What you need to do to assume, to verify that g of x is an inverse of f of x and f of x is an inverse of g of x is you need to take the composition of functions. So let's do f composed with g first. So remember, f composed with g of x, that is f of g of x. So in my function f of x, rather than inputting x, I'm going to import the entire function g of x. So right here for x, rather than just putting x, I'm going to put the entire function of g of x. So this will be equivalent to 2x plus 7 minus 7 over 2. which simplifies down to, well, the positive 7, the minus 7 eliminates, so eliminates down to just 2x over 2, which eliminates down to x. So we know that f composed with g of x gives me x. Now I need to go ahead and verify g composed with f of x. And yes, you do have to do both. So remember, by definition, this is g of f of x. So in my function g, rather than only having x, I am going to substitute in the entire function of f of x. So right here for x, rather than it just being x, I'm going to put my whole f of x, which is all of this monster. Right when we see a fraction, I know we think it's a lot harder than it should be, but it's not. So I'm going to copy down my 2 first. Rather than substituting in x, I'm going to put in f of x, which is x minus 7 over 2. And then I'm just going to copy down my plus 7. So now I need to go ahead and simplify these out. Here you should notice that your 2 on the outside and your 2 on the inside, those eliminate. So it simplifies down to just x minus 7 plus 7. These two eliminate out to 0. So this one does also simplify down to x. So since f composed with g of x is equal to x and g composed with f of x is equal to x, we can then state that yes, these two functions are inverses of one another. Okay, so you also need to know how to do this. You need to know how to, given two functions, can you figure out or determine whether or not they are inverses of one another? And to do that, you need to take the composition of functions. Got it? So this one was a little bit on the simpler side when I'm talking about it from like an algebra standpoint. Let me see here. Do I want to give you guys a harder one? Yeah, why not? Let's give one that's a little bit more algebra involved. So again, the concepts are the same. If anything, it's the algebra here that you need to have strong algebra skills to simplify this one out. So given f of x is going to be equal to x plus 3 over 2x, and then g of x is going to be equal to 3 over 2x minus 1, I want you to go ahead and determine whether or not these two functions are inverses of one another. So we have to take the composition of functions. Remember, this is going to be f composed with g of x. So this will be right here in f of x. Rather than writing x, I need to put this entire thing. So this will be 3 over 2x minus 1. All of this plus 3 over 2x. Do we see what I did there? Again, this goes back into last time's notes. For f of x, rather than just having an x and an x. Oops, oh, sorry, I almost did an overstep here. Right here, you also need to substitute in for x, the 3 over 2x minus 1. See, I'm over here trying to go through this too fast as well. So in my function f of x, I have an x there, there, and there. Rather than just writing the x's, I need to put the entire function of g of x. So this turns into 3 over 2x minus 1 plus 3 over 2 times I see another x, so I need to put the 3 over 2x minus 1. So it's very algebra involved here. So I'm going to go through it. It will be a little bit, it will get a little algebra heavy, so just follow along. In the numerator, I see two fractions that need to be added together. Obviously, well, as you kind of just saw me do, this 3, I changed it to a fraction by putting it over 1. So now I have a fraction being added with a fraction. Remember, you need to get a common denominator if you are going to add fractions. So in this case, I'm going to have to multiply this entire second fraction by 2x minus 1 over 2x minus 1 so that we have a common denominator. So this will turn to 3 over 2x minus 1 plus, in my numerator, that's going to change to a 6x minus 3 over a 2x minus 1. All over down here in the bottom, we're just multiplying out two fractions. So you can think of this as like over 1. You just multiply numerator with numerator, denominator with denominator. So this will turn to 6 over 2x minus 1. Here, in my numerator, I can see that 3 can be combined with this minus 3. I have a positive 3 and a minus 3, so those two eliminate out. So this will turn to just 6 over 2x minus 1 over 6 over 2x minus 1. And if you notice here, this is a complex fraction. But then the way that I have kind of taught you guys in the past to deal with complex fractions is this idea of multiplying in and out. So you multiply the numerator with the denominator of the bottom fraction, and then the denominator with the numerator of the fraction. You do this one first, and then you do this one second. You put this one in the numerator, and then you put the bottom one in the denominator. And I'm going to run out of space here, but hopefully it should work. So this should give us 6 times 2x minus 1 over 6 times 2x minus 1. And then you're going to notice here. Oh, sorry, guys. I just realized that up here, I forgot the x. I'm like, well, something's about to eliminate here. So if you notice here, this should have been a 3 plus a negative 3. Those two still eliminate, but this one should have been a 6x. So this should have been a 6x there. So in the top, when I multiply the top with the bottom, this is a 6x times a 2x minus 1. And then the bottom is the 2x minus 1 times 6. So here, this eliminates with this. The 6 eliminates with the 6. And you are indeed left with just an x. So that is just taking the composition of f composed with g of x. We still need to go ahead and do g composed with f. So this one works. Let's see if the other one works now. The other one was, what was it? G composed with f of x. And let me go ahead and write that definition out. So that would be g of f of x, which simplifies down to 3 over 2. Rather than writing x right here, I need to substitute in my entire function of f of x, which is x plus 3 over 2x. So this will be x plus 3 over 2x. And then I need to just copy down my minus 1. Again, we're going to get some complex fractions going here. But we should be able to do it. This is going to be 3 over here. You should realize that this can eliminate out with this. So you would have x plus 3 over x minus 1. I'm going to bring this off to this side because I'm running out of space. So this would be 3 over x plus 3 over x plus, sorry, not plus, minus 1. And then I could put this as 1 over 1. I need to get a common denominator, so I would multiply the top and the bottom by x. So this would be 3 over x plus 3 minus x over x. This should then give us the positive x, the positive x and the minus x simplify out. So you're left with 3 over x. Again, this is another complex fraction. You can put the numerator over 1. Let's go ahead and multiply our outer numbers first and then put them over our inner numbers. This would be equal to 3x over 3. Here, my 3's eliminate out, and this simplifies down also to x. So you should see here that f composed with g of x and g composed with f of x both simplify down to x. So you can go back to this original question up here and say that yes, these are inverses of one another. Alrighty, so learning or knowing how to find the inverse of a function by following these 4 steps is something that you guys should know how to do, as well as being able to identify the domain of functions. but that's not really anything new, the domain part. And then lastly, verifying inverses. So if I give you two functions, can you tell me whether or not those two functions are inverses of one another by taking the compositions? If they both simplify down to x, then you know that they are inverses. If they did not, I know that I didn't give you guys an example. I just realized right now that I didn't give you guys an example where it doesn't simplify down to x. But if they don't simplify down to x, then you would say that they're not inverses of one another. If you need an example of that in class, just let me know. All right, let me know if you have any questions.